Okay, let's look at some of these example problems. So right here we have a student going down a hill, so that means they're losing height, and they're at a constant speed, which tells us that the kinetic energy is staying the same. So what happens to his gravitational potential energy as he goes down the hill? He's losing height downhill, so his PEG is going down, but his speed is constant, so his KE is the same. Okay, in the next one, we have an amount of work done. They give us this, the 150 joules, on a system, and they give us the force and the time, and they want to know the amount of total energy that that system increases by. Well, if 150 joules of work is done, that is the change in energy, so the answer is 150 joules. In this one, we have a person throwing a ball downward, and it strikes the ground below with 200 joules of kinetic energy. So it's thrown straight down, and that becomes 200 joules. Then the person throws an identical ball with the same speed at the same point. So think about the total energy. The total energy here starts out as PEG initial and KE initial. When the person throws the ball up, the KE initial is the same because it's a scalar quantity, so the direction doesn't matter. Therefore, the total energy is the same. Therefore, the final kinetic energy is also the same. In this problem, we have these cranes that are lifting 1,200 kilogram loads. But the first one does it in 20 seconds and the second one does it in 40 seconds. So the work is the same. However, the power is going to be different because the time is different. So the one that does it in double the time, that's going to be half the power. In this one, we have a baseball, and it's dropped and it falls 10 meters. And it strikes the ground with the kinetic energy of 12 joules. So the amount of mechanical energy that's converted into heat is what? So we start out with a gravitational potential energy, but we don't know what that is. So we can calculate it using mgh. So we figure out the potential energy that we start with. We end with 12 joules of kinetic energy, so we're missing some energy. How much are we missing? Subtract this over, and that gives you the heat lost. In this one, we have a little toy launcher that has a spring in it, and they give us the spring constant. They also tell us how much it's compressed, so that's going to be our x. And the question is, what's the spring potential energy? Well, we know the formula is 1/2 kx squared. They gave us k, the spring constant. They gave us the amount that it's compressed. So we just multiply through, do the math, and you get 0.25 joules. Now, in the next part, it's a little trickier because then they want to know, calculate the maximum speed which the plastic sphere will be launched. Well, it starts with spring potential energy. We know what that is. That spring potential energy is 0.25 joules. Well, what does that spring potential energy turn into? Well, it turns into kinetic energy. So we set our spring potential energy equal to the kinetic. They give us the mass of the ball, and we just solve for V, 2.2 meters per second. In this one, we are given the amount of energy. So we see the joules and we see the word energy. So that tells us how much energy has been expended or work done, and they give us the time. So what are they looking for? They're looking for the power. We know power is work over time. They gave us the energy, that's the work done. They give us the time. We just divide to get 200 watts. In this one, we have a 65 Newton weight, and it's falling this distance of 5.3 meters. And what's the kinetic energy of the weight? So we know that the PEG is converted into KE. So all we need to do is find the PEG that we start with. So to do that, we do mgh. Remember that 65 newtons is the m and the g, that's the mg, multiplied by that. And that PEG, that's going to be the kinetic energy when it gets right before it hits the ground. And for this last one, number 10, it says an object is thrown straight up. So Well, they want to know what's the relationship between the kinetic energy and the height. Well, the kinetic energy, when it leaves the ground, is very large, so we know that our graph has to start out high. So right there, we know it has to be answer number 1. But what happens as it goes higher up into the air? Its kinetic energy decreases until it stops.